So this is the second video in the critical appraisal series, and in this video we're going to take a look at outcome measures. So whenever you're doing any sort of test in the clinical setting or in any sort of setting, you always have a tool that you're going to measure some sort of outcome with, right? For example, in the laboratory setting, you might be looking at cholesterol levels, or in the clinical setting, you might be trying to measure pain. Whatever it is you're looking for, trying to measure, you're always using some sort of tool to do that. And this tool is something that we call an outcome measure. And we always want these outcome measures to be valid, to be reliable. We want them to be sensitive to change, and we also want them to be responsive. And we're going to take a look at those four things in this lecture series, in today's video. But the first thing we want to do is look at the different types of outcome measures that we have. And the first outcome measure that we have is a predictive outcome measure. And what a predictive outcome measure is essentially an instrument, some sort of device, maybe some sort of questionnaire, for example, that's going to help us predict a future event, right? Like for those of you who have taken the MCAT, right? The MCAT is supposed to be predictive of someone who is likely to perform well as a doctor, for example, something like that, or likely to perform well in medical school. Well, the MCAT is therefore a predictive outcome measure, right? And there are several ways we can actually create a predictive outcome measure, and we'll leave that for later when we actually get into the prognosis design. The second form of outcome measure that we have is, whoops, that's say number 2. The second form of outcome measure that we have is discriminative outcome measures. So, discriminative. And discriminative outcome measures are basically instruments or devices or whatever it is that's going to help us put people into different groups. It's going to help us distinguish people maybe with a target condition or without a target condition, right? It's kind of like a diagnostics test, right? And maybe a diagnostic test will use a discriminative measure to help put people into a group with disease and into groups without diseases. And the third type of outcome measure we're going to look at is evaluative outcome measures. And evaluative outcome measures are outcome measures, basically instruments, any sort of devices, or whatever it is that you have. It's a method that's going to help us provide data on the result of an experiment. So maybe we're looking for some sort of change from pre to post intervention, and that's what we use an evaluative outcome measure for, right? And in evaluative outcome measures, we actually have two different types of, two different categories. So we have surrogate outcome measures, and we also have patient-reported outcomes or patient-important outcomes. Well, let's take a look at surrogate outcomes first. So let's move that all the way over here. And essentially, surrogate outcome measures are those outcome measures that aren't exactly directly important to patients, right? But they're believed to predict that outcome that is important to a patient. For example, we can look at heart disease, right? The event of heart disease is going to be important to the patient. But a surrogate outcome measure would be something like cholesterol level. That cholesterol level could predict the event of heart disease. So although heart disease is important, the cholesterol level is surrogate because it's not of direct practical importance to the patient, right? One of the bad things about using surrogate outcome measures for basically using it as an evaluative measure is that it can actually be very misleading, right? It could potentially lead to excess morbidity, excess mortality, but the reason people rely on surrogate outcome measures sometimes is because it's very easy to measure the change across all patients, and it doesn't basically make you wait a long time in order to see the results. Now, if you're going to use a surrogate outcome measure, you want to make sure of a couple of things. The first thing you want to make sure is that your surrogate outcome measure is statistically correlated with the relevant patient-reported outcome, right? So if, for example, I was looking for cholesterol level and my patient-reported outcome that I was trying to predict was falling off a bike, right? That would not be a very good surrogate outcome measure because there's probably no statistical correlation between cholesterol levels and falling off a bike. So you have to make sure that the surrogate outcome that you're measuring or that you're using is at least statistically correlated with the patient-important outcome. And the second thing is that in addition to that strength of association between the two, you want to make sure that there's some consistent evidence that shows that, yes, this surrogate outcome actually is statistically correlated with the patient-important outcome. It's not enough to just have one study say, yeah, we found a correlation. There needs to be established evidence in order to say this surrogate outcome measure is a good outcome measure. And the second one is a patient-important outcome. So patient-important outcomes are those that are directly important to patients. For example, death, like heart attack or heart disease events, and so on and so forth, right? And the advantage to patient-important outcomes over surrogate outcomes is that they're very, very valid. But the fact that they are, what makes them disadvantageous is the fact that they're inefficient, right? And you need to wait a lot longer to see that event actually happen, right? And there are different types of patient-important, there are different ways that we can actually measure patient-important outcomes. Measuring surrogate outcomes is actually pretty simple, right? For example, cholesterol levels could have just been a laboratory test. Well, patient-important outcomes, we're going to use a questionnaire to actually measure these. So let me just erase this off the grid. Okay, so patient-important outcomes, how are we going to go ahead and measure these? Well, these are things that we call quality of life questionnaires, and I'm just going to write them down as QOLs. Quality of life questionnaires are essentially meant to assess the patient-important outcomes. And there are three different types of quality of life questionnaires that we can look at, and the first one is generic. A generic quality of life questionnaire is going to be one that is going to capture just the general health. And it's advantageous in the fact that it can be used to compare the impact of an intervention across several different diseases, right? Because it's a generic quality of life questionnaire. The second type of quality of life questionnaire that we have is a region-specific quality of life questionnaire. Now, region-specific quality of life questionnaires, they focus on just a single region that is affected by diseases. For example, let's say that we have the shoulder region. The region-specific questionnaire is going to focus on any disease that is affecting that shoulder region. And finally, we have a disease-specific questionnaire. And disease-specific questionnaires are basically the most sensitive to change. And one of the reasons why disease-specific questionnaires, which by the way are questionnaires, quality of life questionnaires that are relevant to only a specific disease, right? The reason why these are so sensitive to change, or more sensitive to change than number 2 or number 1, is because they're a lot more specific, right? They're probing just for one type of disease, so you can essentially delve into the disease a lot more. So they're a lot more sensitive to change, but they're disadvantageous compared to generic, for example, in the fact that you really can't compare across diseases well because you're only looking at one form of disease. Okay, so now we've looked at the different types of predictive outcome. Now we've looked at the different types of measurements, right? We've looked at different types of outcome measures. So how do we know that my outcome measure is valid or reliable, right? And that's actually what we're going to look at next. So let me just erase this off the grid. Okay, so this brings us into the discussion of validity and reliability. And these are two things that we're going to need to focus on in order to ensure that our outcome measure is useful, that we should actually be using this outcome measure. So the difference between validity and reliability is a pretty simple one. Validity is essentially, how close does my instrument get me to the true score of the thing that I'm looking for. So for example, let's say that my true mean population value for heart disease, whatever it is 5, right? If I consistently keep, not consistent, let's just say for now, if my value was 4.9, then I've gotten pretty close to my true mean population. So maybe that's a very valid tool, right? But validity is not enough. My ability to show that my measurement comes close to the true value is not enough for an instrument, right? The second thing is reliability, and reliability refers to the precision of your measure. If I keep repeating my measures, right? If I keep repeating my measures, will I continue to get values that are close to 5? For example, maybe I got 4.9 the first time. But what if I got 1 the second time, and I got 0 the third time, and I got 2.1 the third time, or the fourth time? This might show that my tool really isn't that reliable, because I'm not coming up with the same result or something close to the same result over and over again, right? So when I have an instrument, I want to make sure that they're both valid, and I want to make sure that they're also reliable. Now, it's very easy to improve reliability of an instrument, right? Obviously, if you continue to take more and more and more measures, then you're eventually going to get a reliable measure, right? This comes back to the idea of narrowing your confidence interval. The more samples you have, right? Think about it in terms of a population. The greater the sample size you have, the narrower your confidence interval. Well, the more measurements you have, the narrower your confidence interval around the true mean value, right? But if our instrument wasn't valid, then, and let's say that we were getting 3, right? And we were consistently getting 3, 2.9, 2.8, 3.1, and we're consistently getting these values. Well, that's not very close to 5, right? So if our instrument wasn't valid, and we're continually increasing our reliability, we're really not correcting any validity. We're really not correcting our validity. All we're doing is we're increasing our ability to detect the wrong value. So you want to make sure that, again, you're both not only reliable, but you're also valid. That your tool is also valid. So now we can get into how we can actually measure validity, how we can actually measure reliability, and so on and so forth. So let me just erase these things. Okay, so how do we measure validity? Actually, what are the types of validities that we have, first of all? There are 4 types of validities that we could potentially be interested in. So we have face validity, we have content validity, we have criterion validity, and we have construct validity. Whoops. Alrighty. So face validity is essentially a type of validity that measures whether or not your instrument is actually measuring the thing that you're interested in, right? So if you're not valid on the face level, then really what are you measuring, right? Let's say I have a patient and I want to measure their cholesterol levels again. I have face validity if I'm actually measuring their cholesterol level. The second type of validity is content validity. And content validity is, am I capturing a comprehensive view of that thing that I'm interested in? So for example, if I'm looking at cholesterol levels, I want to make sure that I'm measuring all the different types of things that might affect the cholesterol level, right? I want to make sure that I'm capturing a comprehensive picture of cholesterol, and I'm not just saying, okay, I'm going to look at one thing in order to determine cholesterol levels. So content validity exists to the extent that I'm collecting a large amount of information around that construct that I'm interested in. Criterion validity is when we're comparing our existing instrument to something else. So criterion validity, that's something else is the gold standard. So I have criterion validity to the extent that my new outcome measure behaves as expected as compared to the gold standard. And we talked about the gold standard in the first lecture. And construct validity is basically, does it behave as expected to some other type of outcome measures, right? Sometimes things don't actually have gold standards. Like, what's the gold standard for measuring pain, for example? So in this case, we actually have other things, other outcome measures that we can compare our new outcome measure to. And I have construct validity to the extent that my new outcome measure behaves as expected compared to other outcome measures that have already been established by evidence. So, face validity and content validity are quite simple, but we can actually further break down criterion and construct validity. Let's move this up. Whoops. Okay, so we're going to further break these two down. Let me just move this over. Okay, let me just erase this first. Okay, so let's start with criterion validity. There are two different ways we can measure criterion validity, and there are two different types of criterion validity. So we have predictive criterion validity, and we have concurrent criterion validity. Whoops, concurrent criterion validity. And predictive criterion validity is essentially going to measure our ability, our new test's ability, or a new outcome measure's ability to predict whatever is going to come next as compared to our gold standard. And the way that we measure predictive criterion validity is we perform the new test at time 1, and then we perform the gold standard test at time 2. Gold standard. And the measures that we use to report predictive criterion validity are sensitivity, specificity. We can actually also perform regression to measure predictive criterion validity. So again, with predictive criterion validity, you perform your new test at time 1, then you perform your gold standard test at time 2. Concurrent validity, as you might expect the term concurrent, you perform both of the tests at the same time, right? So let's say at time 1, I want to assess the concurrent validity of the test. Well, at time 1, I perform my new test and I perform my gold standard test at the same time. I can also then go to time 2, and I can perform my new test and my gold standard test at the same time. But I'm not going to be measuring any sort of change between the two, right? This is concurrent, meaning that it's going to look at the validity at one point in time. So I can either do it at time 1, I can either do it at time 2, I can even do it at both time 1 and time 2, but I won't be measuring changes. And in this case, the way that I do it is I measure the association between the raw score of the test at time 1 and the raw score of the gold standard test at time 1. And if I find that the scores are similar, if I find the association is great, then I know that my new test is very good, right? And the way that we measure raw associations is by using Pearson's correlation coefficient. So we can use Pearson's R, for example. Or we can use Spearman's rho, right? Spearman's correlation coefficient could also work. Spearman's. Now the difference between these and when you should use Pearson's and when you should use Spearman's, well, Pearson's you're going to use if your data was continuous, and Spearman's you're going to use if your data was categorical. So continuous is something that's on a scale, maybe from 1 to 100, for example. It takes on a lot of different values. Categorical is something that is, for example, split into different types of categories, like severe, let's say non-severe, severe, very severe, and extremely severe. Something like that would be categorical. And there are different things in, there are different categories also within categorical. So you could have nominal and ordinal, where ordinal doesn't have any obvious hierarchy, and nominal has an obvious hierarchy. So for example, the example that I gave, severe, non-severe, severe, very severe, extremely severe, there's obvious hierarchy there, where one is more severe than the other. So Spearman's would be used for categorical data. Pearson's going to be used for continuous data when you're trying to measure concurrent validity. Then we took a look at then we've taken a look at construct validity. So within construct validity, we also have two different things. So I'm going to go ahead and draw a diagram here. Let me just get my pen out. Okay, so I have my construct validity that I looked at. And within construct validity, I'm going to have two more divisions. I'm going to have cross-sectional, cross-sectional construct validity, and I'm also going to have longitudinal construct validity. Longitudinal. And the difference between these two are that this one is pretty analogous to concurrent, right? Cross-sectional is essentially going to measure something at one point in time, whereas longitudinal is going to assess change. So it's going to measure something at 2 points in time, and it's going to assess the association between the change in scores. So you might then be wondering, well, how do I go about measuring cross-sectional? How do I go about measuring longitudinal? And before we can actually look at this, we have to understand that there are actually even more divisions within each of these. So within cross-sectional, we have convergent, we have divergent, and we have known group. And we have the exact same divisions in longitudinal. So convergent cross-sectional construct validity, right, this is the way that I'm going to read it as, is essentially a type of cross-sectional validity. So we're basically measuring something at one point in time, right? So let's say I have two tests, and both of my tests want to measure cholesterol levels again. And I want to measure their convergent cross-sectional construct validity. Well, the fact that they're both measuring cholesterol levels makes them convergent. If two things are measuring the same construct, they are convergent. Because I'm measuring them at one point in time, and I'm going at one point in time, they're going to be cross-sectional. And this is construct because one of my tests is perhaps not a gold standard, but it's still a construct against which I'm going to compare the new test that I'm interested in. So the way that I'm going to measure the association for convergent cross-sectional construct validity is I'm going to measure the association of the raw score between the new test and the existing test. And again, I could use Pearson's correlation coefficient or Spearman's correlation coefficient for continuous and categorical data respectively. Now, divergent cross-sectional construct validity is a little bit different. Let's say I'm going to measure happiness, and let's say I'm measuring happiness with my new test. Well, divergent validity would suggest that I get a construct that is going to measure something that is the opposite of happiness. So let's say depression. If I can measure happiness with my new test, and I can measure depression with my existing construct, and I see that when I measure the raw association between the scores of both of my tests at one point in time, and I see that the raw association is negatively correlated, so while one perhaps increased, the other was perhaps decreasing, then I know that I have divergent cross-sectional construct validity. And then known group cross-sectional construct validity. Well, first of all, known group validity is a type of validity that is assessing people at two different stages in a disease, right? Or two different stages in something. So I'm going to get two people that are, for example, in cholesterol levels. I'm going to get two people that have, or two groups. One group has very, very high cholesterol levels, and the other group doesn't have as high of a cholesterol level, but still has relatively high cholesterol levels. And I'm going to measure the known group validity. Using known group validity, especially in a cross-sectional sense, the way that I measure this is by using a t-test or an ANOVA to measure the validity of a known group cross-sectional construct validity. Now, longitudinal, on the other hand, remember, these were all measuring something at one point in time, so we weren't really able to measure the change in scores. Well, longitudinal validity is going to have the advantage of measuring change. So we have convergent again, divergent, and known group. Now, convergent longitudinal construct validity is very similar to convergent cross-sectional construct validity. We still have two tests that are measuring the exact same thing, but this time I'm going to perform my tests, both of my tests at time 1, and I'm going to perform both of my tests at time 2, and then I'm going to measure the change in score of my new test and the change in score of my existing test, and I'm going to find out whether or not the change was strongly correlated, strongly associated, right? So again, I can use Pearson's correlation coefficient or Spearman's correlation coefficient to measure this. But the difference here from here and here was that here I'm measuring change, and here I'm not measuring change. Here I'm just measuring the raw score. Divergent, same idea. Two tests that are measuring two different things. If I can find that the change was negatively correlated, then I have divergent longitudinal construct validity. Sorry about the noise in the background. And then known group validity again, known group longitudinal construct validity again. You could use a t-test or ANOVA to assess the change in scores. So that's a bunch of different ways that I can measure all the different types of validities that I have. Okay. Now we can jump into reliability. So we've taken a look at validity and what makes the test perhaps reliable and how we can measure its validity. But what about reliability? Well, we can take a look at three different types of reliabilities. So we have, in reliability, we have test-retest reliability. Then we have inter-rater reliability. And then we have intra-rater reliability. Okay, and each of these are forms of reliability as suggested by the name. So for example, let's go into test-retest reliability. And what test-retest reliability is, well, first of all, you have to know that this might have to do with a potential questionnaire, for example. Basically, the patient has to be the one performing the test and test-retest reliability. So think about it this way. Let's say I have a questionnaire. My patient is the one actually performing the questionnaire, right? So I could potentially perform some sort of test-retest reliability on the questionnaire itself. The patient performs the questionnaire at time 1, and then I could get the patient to perform the questionnaire again at time 2, right? But some of the criteria for test-retest reliability include this. So the rater has to be constant, so the person who's giving out the questionnaire should be constant, and the disease needs to be constant. So the disease should not have changed between the two times that I gave out my test in order for me to actually measure test-retest reliability. Obviously, the person is going to have different responses on this in the second time to take the test if their disease state changed, right? So if they have to have a similar disease state in order to measure test-retest reliability. So test-retest reliability is assuming that the rater is constant and that the disease is constant, and that the patient is the one that is performing the test. And then we can see that if the test gave similar answers at both times that the patient took the test, then I might have some sort of reliability. Now, inter-rater reliability is going to be a reliability between different raters. So here the rater is not assumed constant, but the disease is assumed constant, and the test is assumed constant. And this time we're saying, well, any sort of error in reliability is because of the different types of raters that we have. So in inter-rater reliability, again, the disease has to be constant. Obviously, if I'm performing some sort of test with an outcome measurement and the disease is changed between the two different times that my group of raters are testing, then obviously I'm going to come up with different results between time 1 and time 2, right? So I want to make sure that my disease is constant. And then the way that I do this is that I can take my test that is performed by different raters, and I'm going to do it at time 1, and then I can do it again at time 2, time 3, and I can continue to do it to measure my inter-rater reliability, to make sure that my scores are consistent between different raters. And intra-rater reliability is very similar in the fact that the disease has to stay constant for the exact same reason, and the test is assumed constant. But this time we're saying that the error in reliability might be because the individual themselves varies. So intra-rater reliability is measuring the within client variability, whereas inter-rater reliability was measuring the between client variability. So one person at this point is going to perform the same test over a certain period of time to measure whether or not I'm getting the same results. So these are the different types of reliabilities that I can measure. But how do I actually go about reporting the reliability? Like, what kind of statistics can I report to determine or to show that I have reliability? Well, you can report a couple of different statistics, but you have two different types of reliability that you might want to report. And the first type of reliability is relative reliability. Relative reliability is essentially measuring the ability of your test, or the ability of whatever it is, to distinguish between clients. And so we use the ICC, the interclass correlation coefficient, to essentially measure relative reliability. Now you might be wondering, well, why can't I use Pearson's or Spearman's correlation coefficients to demonstrate the reliability, right? If it's my ability to distinguish between clients, why can't I use those two? And the reason for that is because both Pearson's and Spearman's are not able to consider systematic differences between patients, right? But the ICC, and ICC is given by this equation, so ICC equals between client variance over between client variance plus within client variance. The ICC is able to account for the systematic errors that might be present, and thus you might then say, well, measures that are highly associated, right, but are systematically different, will have a correlation coefficient. That is to say, a Pearson's correlation coefficient or a Spearman's correlation coefficient that is going to be larger than our agreement statistics here, so our ICC, for example. We could also potentially use kappa. So kappa is again going to give us the same type of relative reliability measure. Both of these can measure systematic differences. Now let's say measures that are very highly associated and they don't have any systematic differences. Well, now your relative reliability values for ICC and kappa are going to be very similar to your correlation coefficients, like your Pearson's and your Spearman's, right? So that's why you want to use ICC or kappa when you're determining relative reliability. Now, we have actually two different types of kappa. So an ICC is used for continuous data, when you're trying to measure relative reliability for continuous data. And kappa, you have, let's move that down here, kappa you have an unweighted kappa, and you also have a weighted kappa. And an unweighted kappa is used for dichotomous measures, essentially. So potentially things that have two outcomes. So for example, a person could be diseased or non-diseased. Well, weighted kappa is used for some sort of categorical data. So something that might also have some sort of obvious hierarchy, for ordered categories, in other words. So for example, I could have disease that is no disease, mild disease, moderate disease, severe disease. Well, then I'm going to use with a weighted kappa to report the reliability here. So that's relative reliability. Well, I also have absolute reliability. Okay. And absolute reliability is the ability of an instrument to essentially stay consistent. So it's the degree to which repeated measurements vary for individuals. And the way that I'm going to report my absolute reliability is by reporting something called the standard error of measurement. Okay? And I can actually also report my absolute reliability with a confidence interval. And the way that I calculate my confidence interval is that I take my standard error of measurement and I multiply it with the two-sided z of the confidence level that I'm interested in. So for example, if I'm looking for a 95% confidence interval, then I will multiply my standard error of measurement by 1.96. If I'm looking for a 90% confidence interval, then I'm going to multiply by 1.64. If I'm looking for an 80% confidence interval, then I'm going to multiply by 1.28. Okay? So, and basically this is not actually enough for the confidence interval. Before the standard of error measurement, we actually have some sort of point estimate. So let's call that mu, and we're going to plus or minus it. And that's going to be our confidence interval. Okay? And the way that we interpret this, let's, for example, just for the sake of this, say, let me just erase up here to give us some more space. Okay, so let's say that my true mean score was 5, and let's say that I'm looking for a 95% confidence interval. So my z-score associated with that would be 1.96, and my standard error of measurement was, let's say, also 5. Right? Then my confidence interval is going to be 5 plus or minus 5 times 1.96. Right? And this is going to give me my lower boundary of my confidence interval and my upper boundary of the confidence interval, and whatever score that I get, right? Because this is the confidence, this is going to define the margin of error. Whatever score I get, I can say, well, clinicians can be, for example, for this, 95% confidence that the true score is actually within the reported limits, right? So whatever this amounts to, I can say that it's 95% confidence that the true score is within this value. And that's how I'm going to report my standard error measurement, my absolute reliability, and that's why I use that standard error of measurement. Now you might be wondering, well, obviously I can see if patients have changed, right? But what constitutes a true change, and what constitutes a change that perhaps happened only because of chance? That has to do with a minimal detectable change. And we're going to put the value x here, where x represents the confidence level that we're choosing. So let's say we chose a 90% confidence interval. Then this would be an MDC 90. Okay? Essentially, the minimal detectable change is the score that we need to see. Well, someone needs to have a score that is greater than the minimal detectable change in order to be confident that a true change has actually occurred beyond chance. So let's say that, or actually let's actually take a look at the equation first. So again, in order to calculate my minimal detectable change, I again need to use my standard error of measurement. I'm going to multiply it by my z value of interest. So for a 90% confidence interval, we said that was 1.64. And then I'm going to multiply it by square root 2. And this is going to give me my MDC 90. If instead I had this as 1.96, which is what you usually will probably have, then it'll be a MDC 95. But essentially, let's say I got a value, and let's say my MDC 90 was now 11. Well, then I can say that I am 90% confident that the true change has occurred if someone's change exceeds the value of 11. Okay, and that is minimal detectable change. That's how we know whether or not a true change has occurred. So this is actually different than your ability to be sensitive to change, right? And there are many ways that we can report sensitivity to change. So before we were just looking at reliability. So now we've looked at reliability, we've looked at validity. The next thing we want to look at is sensitivity to change. How can we report sensitivity to change, and what exactly is sensitivity to change? And sensitivity to change is the ability to measure any sort of change, right? If your test can't measure any sort of change and you're looking to measure change, well then your test is useless. And the way that we report sensitivity to change is most commonly given as a standardized response mean. And the way that we calculate it is we take the mean change. So we could have mu2 minus mu1, which is the mean follow-up score minus the mean baseline score, and divided by the standard deviation of the change scores. Okay, and that's how we get the standardized response mean. And if our standardized response mean is greater than 1, then we know that we were able to detect some sort of change, right? This is the variability, right? So the greater our variability, the less our ability to detect some sort of change, unless we saw a great change, right? So if we see something, a standardized response mean, for example, that is greater than 1, it means we saw a change that overcame that noise or variability that is represented in our denominator. Now, we can also report responsiveness. So this is the final criteria to assess some sort of outcome measure. And responsiveness is different from sensitivity to change in that sensitivity to change is measuring your ability to measure any change. But responsiveness is measuring your ability to detect a clinically meaningful change. This is where the whole idea of MCIDs are going to come into. So responsiveness, again, is your ability to measure a clinically meaningful change. So you might then say that a measure could potentially be sensitive to change, but it's not necessarily responsive. But a measure that is responsive will always be sensitive to change. Okay? So the statistic that is used to report responsiveness is the MCID, the minimal clinically important difference. And the MCID that you're always going to be, or that you're mostly going to be interested in, is the between group MCID. Usually what you report or what you get is the within group MCID, right? But you're interested in the between group MCID. And the reason for this is because, let's say we have two groups of people. And my first group of people are people that don't have the disease, and my second group of people are people that do have the disease. And they both go through treatment, right? Or let's say, actually, for the sake of explanation, that they both have different forms of, in terms of severity, different severities of the disease. And then they go through treatment. Well, within each of the group, they're going to basically have been expected to change a lot, right? For example, a person who had the disease, went through the treatment, got cured, well, their change was massive. They had the disease, and now they're cured. But for between group MCIDs, right, that change is not going to be as great. If you think about two people from within the same group, right, or between client MCID, whatever you want to take that as, if you think about two people within the same group, well, one person might have improved from their initial condition to some level, and another person improved from their initial condition to the same level, and they may have improved to different levels, but they definitely didn't improve, or not definitely, but they probably didn't improve the same amount, right? But that change wasn't as great as just looking at an individual who changed from initial to the end. So that's why our within group MCID is usually greater than our between group MCID. So when we're doing sample size calculations, you want to be conservative and use that between group MCID, because our between group MCID is a lot smaller, and that's the reason for that, right? Individuals between group change, since post-treatment, individuals are actually expected to vary more than pre-treatment, but they're going to be expected to remain similar to other groups who have undergone the same treatment for the same problem. So that's how we report responsiveness. But how do we actually come up with MCID values? And that's what I said that we're going to come up with. We're going to look at in this video. So there are three different ways that we can come up with this value. First way is by using the anchor-based approach. I'm going to call this the ABA. And what we do with the anchor-based approach is we take patients at time 1 and we take patients at time 2. And between time 1 and time 2, we're going to administer some sort of intervention, and then we're going to measure them at time 1 and oh, whoops-a-daisy. I just realized time 2 is the end. So we're going to measure them at time 1, and then we're going to measure them at time 2, and in between we've given out some sort of intervention. At the very end, we're going to give these patients a global rating of change questionnaire, so GRC, and what we're going to do is we're going to take the GRC and we're going to average the scores of patients who indicated a small but important change on this GRC. So that would be about a score of 2 to 3 on a scale of 1 to 7, and then we're going to average the values. And that average is going to be our within group MCID for that instrument. Okay? So that's what we use, and that GRC is basically the anchor in the anchor-based approach. And that's how we determine, one of the ways that we determine an MCID. But you might just notice that I said that this average is going to represent our within group MCID. So how do I get it to be my between group MCID? Well, there's actually a study done, and it was by Goldsmith et al., and they demonstrated that the between group MCID is 20% of a within group MCID. So what I would do here is I would take my within group MCID and I would multiply it by 0.2 to get my between group MCID. But the anchor-based approach is not the only way that I can come up with my MCID value. I can also come up with an MCID value by using a distribution-based approach. And there are two different methods in the distribution-based approach. So we're going to call this DBA, distribution-based approach. And in method 1, I'm going to essentially look at a population that is not expected to change at all. And let's say that they've gone through a whole bunch of things, but this population didn't go through any sort of intervention, and that's exactly why I'm not expecting them to change. Well, then let's say I gathered from them a standard deviation, I gathered from them a mean score for whatever it is that I was looking for, and I gathered from them, or let's say I'm going to report a 95% confidence interval, so my Z-score is going to be 1.96, right? And then I'm going to calculate a confidence interval. So I'm going to take my mu, my point estimate average for the entire population that is not expected to change here because I didn't give them any sort of treatment. I'm going to calculate my confidence interval by doing this. Right? But because this is a population that I'm not expecting for anyone to change, that I'm not expecting anyone to change in, really I'm only going to be interested in the upper boundary of the confidence interval. I'm going to explain why in a moment, but really I'm only interested in the upper boundary of that confidence interval. So let's say I got a value, and my confidence interval was, let's say, 5 to 15. Okay, so really I'm only interested in this value of the confidence interval. And the reason I say this is because this population is one that was not expected to change, and this value becomes my within group MCID. So what I'm going to say is that a patient who has changed more than 15 is unlikely then to be from this population, right? I'm looking for an upper boundary, looking at the upper boundary for the confidence interval. So anyone that is outside the confidence interval was probably not from this population. So someone who changes more than the confidence interval that is represented for this population that is not expected to change is unlikely to be from this population. And the interpretation, because this is a 95% confidence interval, would be that someone who's changed more than 15 points is less than 5% likely to be from the population that wasn't expected to change. My second approach is by using a population that is expected to change, right? And we have a similar idea. We're just going to use again, we're going to have some sort of mu that we got from them. We have a standard deviation that we got from them, and we're going to report a 95% confidence interval, so we're going to use this Z value. And this time, I'm only concerned with the lower limit of my confidence interval, my lower boundary of my 95% confidence interval, as reflected by that minus sign. And let's say again that I had my confidence interval values and I got 5 to 15. This time I'm only interested in this. And the reason why I'm interested in the lower boundary of the confidence interval this time is because this population was expected to change. So I want it to be very likely that someone who changed more than 5 scores or more than 5 points was definitely from a population that was expected to change. And again, this becomes my within group MCID. So now my interpretation is that there's a greater than 95% chance that someone who changed more than 5 points was actually from this population that was expected to change. Right? And again, both of these approaches are giving me within group MCIDs, and so is that anchor-based approach. So I'm going to multiply by 0.2 to get my between group MCID. Okay? And that is about it for this video. Really nothing else left to talk about in measurement properties. We're actually going to get into study designs in the next video. So the first study design we're going to look at in the next video is an RCT study design. Okay. Again, I hope this helps.